Okay, so for those who aren't satisfied with the basic knowledge you get in a class about mechanical advantage and Hall systems for rope, we can take a deeper dive and get into like the root, like fundamental concepts. It's worth a Google to search for like classes of pulleys and types of pulley systems, because they aren't going to give you the answers that we typically get in like a rope rescue class or even like a structural collapse background. We talk about 3 classes of pulleys and then 3 types of pulley systems. You Google that, you'll get a different answer. They'll call it a fixed pulley, a movable pulley, a compound class of pulley. Mechanical advantage is a ratio expressed as the effort or the input force to the resistance, or vice versa, depending on how you look at it. So it's a ratio of force you have to move or overcome to force applied that moves the load. They're levers. So when we talk about pulleys, pulleys are a subcategory of simple levers. And so the classic lever is your seesaw, just as an analogy. On a seesaw, if you could imagine that the center of your seesaw was the fulcrum on the ground and the 2 people were on the ends, and you draw like a plank between it, it would teeter. And this is where we start. This is your class 1 lever if it was just a seesaw, but now we have a continuous lever, so a class 1 pulley. What class 1 means is if the input is my hand here and the resistance is the opposite side, the fulcrum is at the middle. So the fulcrum is between the input and the resistance, or the Hall team and the load. That's what class 1 means. For pulleys, there are some additional special characteristics, because we could do this on flat ground, put like a fulcrum, and then we could change the distance on each side depending on where we want to put that plank. And what defines mechanical advantage is it's the ratio of the distance away that resistance is to the fulcrum in relation to, or as a ratio of the distance away the input is to the fulcrum, regardless of where any of that is. Here in pulleys, since we don't have the ability to change the shape, we can't like make an in rope rescue, we don't make an elliptical pulley. It's a perfect circle with an axle going through the center. And so the relationship is always going to be some factor of 1, 2, or half, depending on where things line up. In a class 1 pulley, since the fulcrum is the axle and it's always at the center between the 2 that are on the outsides, if you look at the distance between the load or the resistance to the fulcrum, I'm going to call that 1 unit. And I'm going to relate that to the distance between my Hall or input to the fulcrum, also 1 unit. So the ratio of mechanical advantage to the class 1 pulley is 1:1. For practical sense, the telltale sign that it's a class 1 pulley and no mechanical advantage is generated because the ratio is always going to be 1:1. It's a stationary pulley at an anchor. It doesn't move. It doesn't matter like if this is 180 degree bend or not. I can stretch this out, it becomes a directional, but the distance between the 2 in relation to the fulcrum is always the same. So it's a 1:1 mechanical advantage. So class 1 pulley is a specific type of class 1 lever where the mechanical advantage is always 1:1 or no mechanical advantage at all. It's a simple change of direction. It's stationary, it does not move. Because we can generate mechanical advantage even if it's a class 1 lever, but not a pulley because of the geometry or the relationship between distance and force for the both halves of the system. So work in is work out. No matter how much mechanical advantage you create or mechanical disadvantage you create, the work will always be the same. In theory, now we're disregarding friction, so we throw friction loss in there, it changes things. But for simplicity's sake, work will always be the same. Work in equals work out. Work is force times some sort of distance or length, regardless of what it is. Pulleys, levers, it's all the same. Where we generate mechanical advantage in a pulley system comes from the next type of, or the next class of pulley. You're thinking, oh wait, if the rope terminates at the anchor, it's even or odd. We aren't there. We aren't talking about that yet. There are, and this is where that splitting tension comes into play, right? My hand is holding the load that is suspended at the axle of the pulley, but the axle is no longer the fulcrum. If I just took my hand and tied this off to the rigging plate and everything was static, you could say that 2 strands support this load. So if this load's 100 pounds, I have 50 pounds in one strand and 50 pounds in the other strand. It splits it. So splitting tension is one of those things that we hear a lot. If I took my hand and pulled this up together, it stays the same. It's still a 50-50 split on the 2 strands. But now I'm doing the same thing, but I'm only pulling one strand and it's a continuous lever. So one side's static, it bears half of the weight, so 50 pounds if it's 100 pounds, so 50% the entire time, and I pull the entire time with 50%. So let's look at what's going on with the actual pulley and talk about where the fulcrum is, where the resistance is, and where the input, or like my haul, is. So the load is suspended at the axle. So the axle is no longer the fulcrum. The fulcrum is what we're levering against. That's fixed. So when we look at where the fulcrum is, this line is always fixed, it's not moving. So the fulcrum is always gonna be, if we take our plank and redraw it right here level, our fulcrum is here, so it moved. In a class 1 pulley, our fulcrum was at the axle, but now our fulcrum is all the way to one side. And our load is exactly 1 unit centered. I'm gonna call it 1 unit over. That's where our load is, or our resistance. And the applied force or input, or the haul team, is exactly 2 units over. So this is an inherent 2-to-1 mechanical advantage system. And that is like the basic building blocks of your rope rescue pulley systems. They always generate a 2-to-1 mechanical advantage system because of the limitations of it, the perfect circle of a pulley, and that the fact that the axle is always dead center, it will always be 2-to-1. That's assuming that I haul a complete 180 or pi bend. The second I haul out at an angle this way, I shorten my input lever in relation to the fulcrum, and I'm not as efficient. So if I'm hauling way out to the side here, it's more like a 1.5. And then if right now there's nothing, this thing just slides down, and if I'm going straight down, I bring it up, and then I start to utilize the leverage. And the max utilization of the leverage I can get is a complete 180-degree turn through that pulley. This is a class 2 lever because the resistance is between the applied force and the fulcrum. So that's what defines a class 2 lever, specifically a class 2 pulley. And the characteristics of a class 2 pulley are always a 2-to-1 mechanical advantage. And it's moving. So it's not a stationary pulley. The telltale sign that, oh, you have a class 2 pulley that generates mechanical advantage is it moves in relation to the anchor. We split tension. We're splitting tension. 50%, 50%. If I had 3 strands going here supporting it, that would be a 3-to-1. Let's do a class 3 pulley, which we don't really see in rescue all that often. We have a kettlebell, which I'm gonna consider the anchor. This is my load. And our rope is anchored to the ground, comes up to a pulley that moves. Now I have to haul. And when I haul, a couple things happen. So I'm hauling, but look at the rate that the weight or the load moves in relation to how much I have to haul. I'm actually hauling more than the weight itself. So it's a mechanical disadvantage, but I'm generating twice the speed. These have other applications in like structural collapse or stage rigging, but for rope rescue systems, we don't use them very often. We have, this is attached to the kettlebell. This is anchored. So this is our fulcrum. Our input comes from my strand, but that's just a directional. So it's going through a class 1 pulley. No mechanical advantage generated up here, so 1-to-1 up here, but this is the applied force or my input. It's going along the spine of the carabiner, it's at the axle of the pulley. So what defines class 3 systems is where our applied force or haul force is located between the fulcrum and the load, or what we want to move, the resistance right here. My input or my haul is located at 1 unit away from the fulcrum, and the load is located at 2 units away from the fulcrum. So my mechanical advantage is 1 unit to 2 units, or 1 to 2. That simplifies down to mechanical disadvantage at 0.5 or 1/2. So why would this be advantageous for me if it's a mechanical disadvantage? It's a class 3 lever or class 3 pulley. And the reason is, if I had plenty of input power, I don't care about mechanical advantage. Where I gain is in the speed of lift on the load. So that's where, like, aerial apparatus, your hydraulic rams, they can lift this ladder really fast with a lot of hydraulic force, because they can do that. They're capable of doing that. So if we want to lift things really fast and we don't care about like how much force we have to create to do that, all we care about is the speed of lift. So stage riggers will do this. Some people would also get confused with class 3 pulleys because they think, oh, it's also a differential. Well, yes and no. It's not quite a differential, because a differential could also have the characteristics of a class 1 pulley at the anchor. So I coined differential pulleys as class 4 pulleys. I haven't heard that anywhere else, so I just arbitrarily made it out of thin air, but I like it because when I say class 4, that will delineate the confusion between, oh, wait, a differential is a class 3. Well, no, not necessarily. If it's at an anchor, it's just equalizing. Class 3 pulley will always generate a mechanical disadvantage in an inherent ratio of 0.5 to 1, or 1/2. So you're having to pull twice the force, but you get double the speed. So those are the 3 classes of pulleys. Not to be confused with the 3 types of pulley systems. Those are the simple, compound, and complex pulley systems that I've covered in other videos. But at its root, mechanical advantage, we have 3 classes of levers. Subcategories are the pulleys, 3 classes of pulleys that have specific characteristics, assuming that the rope enters and exits a 180-degree bend. Class 1 pulleys generate no mechanical advantage. The ratio is always 1 to 1 and they're stationary. Class 2 pulleys are traveling pulleys, and they will always generate a 2 to 1 mechanical advantage. Class 3 pulleys always generate mechanical disadvantage at 0.5 to 1 ratio. So not to be confused with a differential. Whether that's simple, compound, or complex, like fundamentally, a moving pulley is what generates mechanical advantage, and it's a 2 to 1. But what about your classic 3 to 1 Z-rigs? So we have our weight down here, whatever, this rope grab, this whole thing could be at the lobe too, but usually in rescue, like, we send a line over and like the edge is somewhere right here. So let's look at this idea of splitting tension. So if I took my hand, took all these strands and just tied them into the load, and they're all like, it's 3 strands supporting the load, and I pull up on these 3 strands, each one of those strands is at about 33.33% of the load. So they're splitting the tension. That's no different with mechanical advantage, except I don't have to pull on all 3 strands. I just pull on the 1 strand here, and it's a continuous lever effect. So there's a 2 to 1 being generated through here onto this rope grab, but it's not a 2 to 1 for the system, because there's the additional tension that this goes through your traveling, or sorry, your stationary class 1 pulley down here, and that's where you do the T method. That's where the T method comes from. You add 2 units to 1 unit, you get 3 units here, and then 1 unit on the load. I'm just gonna pull down through a change of direction so it's easier for me, and that's your simple 3 to 1 system with a capture. So splitting tension. How many strands support the load directly? It's 3. We have 2 class 1 stationary non-moving pulleys that don't generate any mechanical advantage, and the 1 class 2 moving pulley that generates a 2 to 1, but it's a 3 to 1 system because of that additional line that's holding that tension. So splitting tension, or with 3 strands. That's also like a good kind of definition for the input source rule, the frame of reference rule. So if this kettlebell were me and I was hoisting myself, you have to think about now, well, how many strands directly support the load? It's not 3, because the input is not going, yeah, it's going through a change of direction, but it's coming back to the load. And so the load is doing the work itself. And now you, instead of having 3 strands that directly support the load, it's actually 4. So it's just one of those weird things, going back to like simple mechanical advantage, the number of strands that directly support the load is your mechanical advantage. So if someone else is doing the hauling on the ground and I'm the kettlebell being suspended, then that will be a 3-to-1 with a final change of direction. But if I took over the haul, it directly supports me as well now. And now it's a 4-to-1 with no change of direction if I'm hauling myself up. Okay, I don't think I would do it justice talking about the fundamentals of pulley systems without talking about friction. I mentioned it at the start of the video. It all goes back to belt friction theory, the capstan equation. I'm using the Maestro because the sheave it only spins in one direction. So on the haul, it's a pulley, but right now, if I lower out, it's basically just like a tree or a drum that doesn't move. And so there's some friction in here. And so when I release and I let the rope move around the drum, there's friction being absorbed in here. So if this drum didn't move on the haul and it was stationary and I was pulling, I would have to overcome the friction that's generated or that's absorbed in here. And it's like, well, what is that friction? What's the relationship? What does that mean? Well, there's this thing called the capstan equation, and it says that the tension I have to overcome, or my input force, my haul tension, is going to equal the tension that's on this side, or if it's suspended in mid-space, just the load, times basically the friction loss. And we have to figure out, well, what is that friction loss? What's the relationship? It's exponential. It has to do with the actual coefficient of friction between the material properties. So whether it's nylon or polyester rope, that coefficient between, if it's a steel, aluminum, metal, so it's a number that they generate or determine through testing, and the angle change, the cumulative angle change. So tensionless hitches, if you keep on winding it around a tree, that's cumulative bends, or cumulative angles. Most of our pulley systems or haul systems, our rope is going in one direction and going through a complete 180-degree bend or pie out the other way. So we can't really change that angle. It has an exponential effect on friction, but we can't do anything about that. What's killing us in that regard is the material property, the coefficients between the two materials. That actually helps us when we have a non-moving pulley on a lower. We can use that to our advantage to help us control the rate of the lower. It kills us on the haul. On the haul, now we start to put in pulley systems, because what pulley systems do for us is they change the coefficient of friction. The coefficient of friction is no longer the rope on the material. Granted, it's touching the material, but it's moving with the material. So if I haul on this, it moves with the material. And the coefficient of friction is no longer here. It's actually the relationship between the little ball bearings that are sealed and lubricated, that actually makes it even more slippery and slick, and the axle. So that we drop that coefficient of friction way low, and it gives us a higher efficiency, or pulling efficiency. Yeah, we still lose some, but it's better than a carabiner, or it's just better than wrapping this around like a tree branch or something. And that's the capstan equation. It explains a lot in terms of lowering devices, belay devices, friction devices, tensionless hitches. Even explains like the strength of knots and where the weak point in a knot is. Capstan equation. The tension I have to pull is equal to the tension on the load times E, which is Euler's constant. It's like 2.7 to the power of the coefficient of friction times the total bend, expressed as radians. In theory, I don't know if it's true in real life because I haven't done any testing on it, but nowhere in the capstan equation does it talk about surface area. So actual surface contact area, it's negligible, which is probably why you can take a rope and lay it on a street, and it's like 600 feet of rope, and you go and you just take the end of that rope and you can just pull it, because yeah, the coefficient of friction is there, but there is no bend. It's just a straight pull on a rope that has a lot of surface area in contact with the pavement, but that's not part of the capstan equation. If it was, then you wouldn't be able to pull on that rope. This pulley and this rope, it could be really small, or this could be the size of a house, and it wouldn't change the friction. It's not in the equation. In reality, does it? I don't know. I haven't done any testing, but surface area is not a factor in friction. And some books talk about how you want to match up your rope diameter with the pulley sheave diameter for to maximize, really just to maximize the strength of your rope. And some books say, oh, you want your pulley to be 3 times the diameter of your rope. Other books will say 4 times the diameter. Within reason to maximize your rope strength, because it's a more gradual bend. There are a bunch of strands in here, and the outermost strands as it wraps around are under tension, and the innermost strands as it wraps around are being compressed. And so to simplify it, you could just say, that's why with knots, you just arbitrarily, just for planning factors, when you tie a knot, you create this bend and you just say, oh, it's 50% derating on the strength of your rope. Because of that bend, the strands inside, the outer ones have to stretch and they're under tension, while the inner ones compress and they're under no tension. It's basically kind of like cutting your strength in half. That's why they say, okay, 3-to-1 or 4-to-1 ratio between the diameter of your pulley and your rope is ideal. Is it critical? I don't think so. It's more like one of those gee whiz, good to know things. I think some other manufacturers of marine ropes and some other places, people that make like sewn eyelets and stuff, go as high as 8-to-1. If you truly want full, legitimate, like rope strength, 100%, 8-to-1, that's a pretty big ratio. That would be a huge pulley, completely impractical. Anywhere between, I'd say like 1 inch to 2 inches for rope rescue is probably appropriate. And it doesn't really matter. Like, if you're worried about the strength loss, you must be doing something really wrong, because you must be moving more load than you should be. Earlier in the video, we talked about like the fulcrum and the applied force or input or effort against the resistance or the load, and said that, oh, it's always some factor of half or 1 or 2 because everything's symmetrical. When we start to get into like more detail, it's like, well, yeah, that was for simplicity, but what we aren't accounting for, just to make our lives easier, is we're assuming that like we aren't taking into account the diameter of the axle. We said that, you know, if my load is here and my input is over here, it's the distance between the resistance to the axle being dead center is 1 unit, and then 1 unit between my input or my haul team to the dead center of the axle. But it's not dead center of the axle. It's actually, if I'm hauling, my input is at the edge there for sure, but the resistance is actually at the opposite edge of where that axle is. So the smaller the axle, the more efficient our pulley. The bigger the axle, so if like our ball bearings were all up in here and this axle was really big, the resistance is actually on the edge, the outer edge of that axle, and it makes it less efficient. But do we care? No, because those are manufacturer's problems. We buy the best pulleys we can and we just deal with that. We just make our lives simpler for ourselves, and we just assume that, okay, we're just gonna do the theoretical numbers. But just know that the bigger the axle, the less efficient your pulley. The smaller the axle, the more efficient your pulley, all other things being equal. So, thanks for watching. Hopefully I didn't confuse you too much. Yeah, you can get really into the weeds with this stuff, and at the end of the day, is it going to change kind of what you do on a rescue or how you rig stuff? I don't know. Maybe not. You just take it for what it is. If you like it, great. If not, I don't care.